Hello and welcome back. In this video, we are going to derive the pi molecular orbitals of 1,3-butadiene using the projection operator method. Here we have sketched the carbon skeleton of 1,3-butadiene. This compound is a prototypical diene in the Diels-Alder reaction. In such reaction, it must exist in the s-cis conformation, and it's for that reason that we are going to derive the orbitals for this particular configuration. Butadiene is a planar compound, and we imagine it to be in the exact same plane as the whiteboard. Going vertically on the whiteboard is the z-axis, and going to the right is the x-axis. That leaves the remaining y-axis as coming directly out of the whiteboard. We notice the alteration of double bonds and single bonds. Therefore, we expect the phenomenon of resonance, and we expect the pi system to be delocalized over all 4 carbons, each carbon contributing one pz orbital to the pi system. We have lightly sketched in the relevant p orbitals on carbon. We've shown them at an angle. This is to infer that they would be pointing out of the board, so that they are perpendicular to the plane of the whiteboard. And we have labeled them P1, P2, P3, and P4. Something that's very important to keep in mind is that the orbitals involved here are p orbitals. Therefore, they have alternating phases. The 2 different lobes will have opposite polarities. We have not shown that here, but that will be a critical feature in our derivation. The molecule has the point group symmetry of C2V. One feature by convention for the point group C2V is to make the high order rotation axis, which is a C2, be synonymous with the z-axis. As a result, these p orbitals on carbon are effectively 2py's as opposed to the more usual nomenclature to refer to them as the 2pz's. So it's not going to make a difference. It just, we've altered our terminology consistent with the general usage in the point group C2V. Now we need to generate a reducible representation for pi bonding in this molecule. And as a result, we make a table, and we have a single column for each class in the point group C2V. Because C2V is an abelian group, each operation is its own class. So therefore, we have a column for every single operation in the group. The character for this representation for pi bonding is equivalent to finding the number of p orbitals that don't move under each of these symmetry operations. That's how we find the particular character. For the E operation, each of the orbitals stays exactly where it is, so therefore our character is a 4. For the C2 operation, its rotation around this axis, which would take P1 to minus P4, it would take P2 to minus P3, and so on. So every single orbital would move. Since all the orbitals move, none stays put, so therefore the character is a 0. Our third operation is a mirror plane. This should be a V here. So it's a vertical mirror in the plane of the whiteboard, since it's the x-axis. So therefore it reflects the top of the molecule into the bottom. So P1 gets reflected into the bottom of P1, and so on. But recall that the p orbitals have opposite phase, so the positive phase at the top of the orbital is getting reflected into the negative phase at the bottom. So because we have this change of phase, even though the orbitals stay in place, we write this down as a -4 character. So this is a peculiarity of pi bonding that we do not have in sigma bonding. Finally, we have the vertical mirror for the YZ plane. So that's a plane going like this, where it reflects the left side of the molecule into the right-hand side. that moves all of the orbitals to some other place, so therefore the character is going to be a 0. And we now have a reducible representation for pi bonding in this molecule. To reduce the reducible representation, we have a conventional formula that we use. We go one by one through the irreducible representations in the point group C2V. There are 4 such irreducible representations, so we have to perform 4 different calculations. The first part of the calculation is always we have a division by the number of operations in the group. There are 4 operations in the group, so we have this 1 over 4 that we begin with. We can consider multiplying by 1 over 4 or dividing by 4. And now we have a series of terms. The first character in each term is going to be the character from the reducible representation, which here is a 4. And we multiply it by the corresponding character for the operation and the irreducible representation in the point group. And the character here is a 1, so therefore we multiply by a 1. We notice now that we have a 0. We have 2 different zeros. Since we multiply anything by a 0, we get a 0. We can effectively ignore any of the characters that are equal to 0, and we can move on to the second non-zero character, which is our minus 4. So we have plus, so we have minus 4. And now we multiply this by the character in the character table, which for A1 is going to be a positive 1. And then this is our calculation. So we have 4 minus 4 is 0. So the result of the calculation being a 0 tells us that we don't have any A1s, any A1 irreducible representations that make up the reducible representation gamma sub pi. And now we move on to the second irreducible representation, which is called A2. Again, we have our 1 divided by 4. And we can save labor by writing down parts of the calculation which will not change. So for every single step, the characters from the reducible representation will not change. So we have the 4 and the minus 4, which we write down, and we've color-coded in blue to remind us where those came from. And then we write down the characters from the character table for C2V, and these will change. So the first is a 1, and the second one is a minus 1. So now we have 4 plus 4 is 8, divided by 4, which gives us 2. Which tells us that there are 2 copies of the A2 irreducible representation in the gamma sub pi reducible representation. The third irreducible representation that we have to deal with is called B1. Again, we have our 1 over 4. And again, we can write down the blue characters because they will not change. So we have a 4 and a minus 4. And now we put in the characters from the character table, which in this case turn out to be a 1 and a positive 1 again. 4 minus 4 is 0, so we have 0 copies of B1 in the reducible representation. Last but not least, we have B2, and we have our 1 over 4. You can write down the characters that don't change. So this is a good practice because it makes it much less likely that you'll make an error continually figuring out what numbers to write down. If you know the numbers don't change, it's helpful to write them all down in sort of a series and less likely to make a mistake that way. So then our characters here are 1 and a minus 1. We get this from consulting the character table for the point group C2V, which we can find in our textbooks, and they're widely available online. 4 plus 4 is 8, divided by 4 gives us 2. So what this tells us is that we can write gamma sub pi as a linear combination 2a2 plus 2b2. So let's kind of confirm what that is. So write gamma pi. We can write as 2a2s plus 2b2s. In the next step, we'll show how we can use this information to get an idea of what the molecular orbitals of butadiene actually look like. So now we construct another table, which would need to make one column for every symmetry operation in the group. And we want to see what each operation does to a representative orbital. Now, a challenge in 1,3-butadiene is that we have more than one type of p orbital. We have the type around p1, and then we have a type around p2. These are distinct from each other because there's no symmetry operation which will transform p1 into p2. If we were doing C13 NMR, we would notice that this carbon and that carbon had different chemical shifts. So we need to make an entry for p1 and also an entry for p2 because they are not equivalent. So now let's see how they are transformed by the various symmetry operations. So p1 under the identity operation stays exactly where it is, so that's p1. For C2, it's going to flip around this axis. So P1 goes to P4, but in the process, it's going to change phase. So we write that down as minus P4. The sigma V for XZ is the plane of the whiteboard. So that takes the top of the p orbital into the bottom of the p orbital. So therefore, it's going to change phase, and that gives us minus P1. And then last but not least, we have a mirror plane here, which transforms P1 into P4. We do similar calculations now for P2. The symmetry operation transforms P2 into P2, stays right where it is. The C2 operation takes P2 to P3, but flips it over in the process, so we get minus P3. The mirror plane of the board takes the top of P2 into the bottom of P2, so that's a minus P2. And then last but not least, the YZ mirror plane takes P2 into P3. If you're not sure whether you need to make multiple rows, notice something here, that if we just had P1, the entries that we get here are versions of P1 and P4. We never see P2 or P3. Similarly, for the P2 entry, we get P2s and P3s, but no 1s or P4s. This is definitive proof that P1 and P2 are symmetry inequivalent. Now, for convenience, in our table, we're going to put two more rows that correspond to the irreducible representations A2 and B2. Recall that our pi bonding here was a linear combination of A2s and B2s. And we're just going to copy down the entries in the character table so that we don't have to refer to it later. So remind ourselves that the values are going to be 1, 1, minus 1, and minus 1 for the A2 irreducible representation. Then for B2, the characters are 1, minus 1, and then positive 1 again. Now we will generate algebraic expressions for the various molecular orbitals. To do that, we apply the projection operator technique, and we multiply each entry in the A2 row times the appropriate value in either the P1 or the P2 row, and add all those entries together. So for the first row, P1, you multiply P1 times 1, then we add to that minus P4 times 1, and so on for each of the entries and add them together. When we do that, we see that we get P1 minus P4 plus P1 minus P4. And we can combine and reduce to lowest terms because we're going to make adjustments in the normalization constant at the very end. So we can write this simply as P1 minus P4. We can apply the same process to the second row, P2, for the A2 irreducible representation. So now we have 1 times P2 plus 1 times minus P3, and so on. And that gives us P2 minus P3 plus P2 minus P3. And again, we can condense this down to P2 minus P3. So this gives us two of the two A2 entries that we found when we reduced the reducible representation. So simply now we can use it for B2, except now we're going to multiply each of the entries in the P1 or the P2 rows by the corresponding character in the B2 row. So for the first case, for P1, this gives us, we have P1 minus P4, sorry, P1 plus P4, plus P1 plus P4. And we can reduce that to P1 plus P4. Then for the second B2 combination, we multiply by the entries for the P2 row. So we have 1 times P2 times P3. So that's going to give us P2 plus P3 plus P2 plus P3. And we can simplify as before to P2 plus P3. Now a challenging feature of this is that we have 2 A2s and 2 B2s. Important thing to realize is that we can make interpretations of the orbitals based upon their coefficients. If the two values have the same sign, so they're both positive or both negative, that tells us that they have the same phase. If they have different signs, that tells us that they have different phases. So what we need to do now for A2 is to make the two possible combinations of P1 minus P4 and P2 minus P3. So the first way to do that is to simply add these two together. So the first combination we'll show will give us P1 minus P4 plus P2 minus P3, which we could write maybe a little more elegantly as P1 plus P2 minus P3 minus P4. So we made a linear combination where we kept the phases exactly as we had them before. So the second possibility is to keep the first one with the phases that it has, but now flip the phases of the second one. This is equivalent to subtracting P2 minus P3 quantity from P1 minus P4. Let's see what that gives us. That gives us P1 minus P2 plus P3 minus P4. We can leave that exactly as is because it looks pretty elegant the way it is. So we notice this gave us a different combination than the first combination where we added them together. We can do a similar process with B2. So first, let's simply keep the phases as they're written and add them together. And this will give us P1 plus P4 plus P2 plus P3, which is P1 plus P2 plus P3 plus P4. They're all exactly in the same phase. And now the combination where we subtract, we flip the phases of P2 and P3 from those of P1 and P4. So that gives us P1 plus P4 minus P2 minus P3, which gives us P1 minus P2 minus P3 plus P4. And notice that we have, even though we have these combinations of pluses and minuses, we have not, equal their sign, we have not duplicated any of the previous combinations. So these are the 4 distinct pi molecular orbitals of butadiene. In the next step, we're going to erase some of this other stuff we have on the board, keep what we have here, and show that we can make a visual representation of what these orbitals look like. So let's start with the first combination, the P1 plus P2 minus P3 plus minus P4, and see what that looks like. So we can make a quick sketch of the 4 p orbitals. We'll just draw them in a line just to make it easier here. And the key feature is that we notice that P1 and P2 have positive phase. So we'll put the positive phase on top. And P3 and P4 have a negative coefficient. So that means that they have the negative phase on top. So we can represent the orbital in a schematic this way. An important feature of this is we notice that going from P2 to P3, we have a change in sign. So therefore, since it goes from a positive phase to a negative phase, and it's a continuous function, it must have gone through 0. Points where the molecular orbital goes through 0 we call a node. So this particular A2 orbital has a single node. Continuing, for the second A2, we have P1 minus P2 plus P3 minus P4. So again, we can sketch out our p orbitals here. So we notice that orbitals 1 and 3 have positive phase. So we'll put the filled in at the top. 2 and 4 have negative coefficients, so we'll assume them to have negative phase on top. That means they must have the positive phase on the bottom. So this is a nice, quick way to represent the second A2 orbital. And the thing to notice here is that we have a series of events where we go from a positive, negative, positive, negative. So this has 3 nodes. Continuing for the first of the B2s, we have P1 plus P2 plus 3 plus P4. So they all have a positive coefficient. So that tells us that they are all completely in phase with each other. So we'll put the positive phase on top here. And since we have no changes of phase, this particular orbital has no nodes at all. Then for our final entry, B2, P1 minus P2 minus P3 plus P4, we notice that P1 and P4 have a positive coefficient. So let's sketch this out very quickly here. Since they have positive coefficient, we'll put the positive phase on top. 2 and 3 have negative coefficients, so we'll put the positive phase on the bottom. So here we notice that we have 2 locations where we go from positive to negative phase, so therefore we must have gone through 0. So we have a node there and a node here. So now we've taken our algebraic representations of the orbitals and then put them into a more visual representation over here, and we've noticed the number and location of the orbital nodes. The final step of our derivation is to make use of the visual and algebraic information that we have to put the molecular orbitals in order of their energy from lowest to highest. The principle that we're going to use is that the greater the number of nodes, the higher in energy a molecular orbital will be. We know in this particular case we have no degeneracy because the high order rotation axis is only a 2. We would need at least a 3 to have degeneracy. So therefore each of these molecular orbitals has a distinct different energy. The lowest energy we notice is the orbital that has no nodes, this particular B2 combination. And here, since it's lowest in energy, we've sketched first at the bottom of our diagram, our potential energy diagram, with the sketch and with the algebraic representation. And let's also put down its symmetry label, which is B2. What is going to be the second highest in energy? The next highest in energy. Well, we started with 0 nodes, so we would expect that the next highest in energy orbital would be the one with 1 node. And we have this particular A2 combination that has 1 node, so therefore we're going to place it in our diagram as the next highest energy. And we have put in our table with its symmetry label, our little sketch of it. In fact, even let's put our 1 node in there to remind us that it has 1 node. And then in green we have our algebraic representation that we had derived over here. So after 1 node, we would expect that the next highest energy orbital would have 2 nodes. And we have just one of those orbitals left, this particular B2 combination. And we have placed it appropriately in our energy level diagram with its symmetry label, our sketch showing its phase relationships as well as the nodes, and in green its geometric algebraic representation. Finally, we have one final orbital, which is going to be the highest in energy, and that is the one with the 3 nodes. And lastly, we fill in our table with the highest energy molecular orbital. We can see the 3 nodes, its symmetry label, and its algebraic representation. We have one final task remaining. We keep in mind that to make up this pi conjugated system, we started with 4 p orbitals on carbon. Each one of those is going to contribute 1 pi electron. So we have a total of 4 pi electrons to put into our system. We can apply the molecular version of the Pauli exclusion principle in that we can put 2 electrons into each orbital so long as they have opposite spins. So we start at the bottom, the Aufbau principle, and we put the first 2 pi electrons. And then we move to the A2 level here and put the second set of 2 pi electrons. So you've allocated 4 pi electrons, and we notice that in the process we filled up exactly half of the pi molecular orbitals, which will be relevant for anyone looking at reactions like the Diels-Alder reaction. We notice there's a particular symmetry pattern to the p orbitals in the A2 combination here, which is the highest occupied molecular orbital. This is generally the orbital that's involved in a Diels-Alder reaction for the diene. And butadiene is about the simplest diene we come up with. So here we see what the orbital pattern would be for its reaction with the dienophile. I thank you very much for your kind attention. As always, have a good one.